Thank you all for attending this session of the Brain Science Speaker Series presented by LSU's Multidisciplinary Initiative for Neuroscience Discovery. lsumind aims to coordinate and strengthen neuroscience research, education, and community outreach here at LSU. And my name is Mark Dalecki. I serve on the executive committee for lsumind along with Melissa Beck, Susan Duncan, and Heather Lucas. As usual, we would like to thank the Center for Computation and Technology for funding the Brain Science Speaker Series. And we will be hosting another speaker in the spring, so please stay tuned to the lsumind website or sign up on our mailing list. And it is my great pleasure to introduce today's Brain Science Series speaker, Dr. Taras Lee, for our first talk event this fall. And Dr. Lee is an assistant professor of psychology in the Department of Psychology at the University of Michigan. And Dr. Lee received his Bachelor of Science in Symbolic Systems with a concentration in neuroscience from Stanford University in California back in 2005, followed by a PhD in psychology with a concentration in cognition, brain, and behavior from the University of California in Berkeley in 2012. Where he was working under the supervision of Mark Desposito, German tongue twister for me. And Dr. Lee pursued postdoctoral training at the University of California in Santa Barbara in the Department of Psychological and Brain Sciences under the supervision of Scott Grafton, and in the Department of Psychology at the University of Michigan before he started his current position at the University of Michigan in 2017. And Dr. Lee's and Taras' research focuses on the cognitive and neural processes that contribute to learning, motivation, control, and performance in a variety of contexts, including motor skill learning, expertise, and the phenomenon of choking under pressure. And he published his work already in top tier and pretty high impact journals in our field, for example, Journal of Neurophysiology and also Neuroimage. And we are planning on a presentation of 45 minutes, followed by a discussion. And we have a chat room here, where a Q&A forum where you can put in some questions during the talk. And if I understood it correctly, there's also like a raise hand option, and I could try to give you the power that you can talk and or show your video if you want to talk directly to Dr. Lee. And the current plan is to have this 45-minute talk presentation and then to have the discussion. But if there is something urgent, Taras mentioned already that he's pretty good and okay with also taking questions during his talk. And you guys could also let me know if I forgot something important, but we could ask if Taras may share his screen already, that I remember about the talk title exactly. And yeah, I look very much forward to his talk, which is titled Motivation, Cognition, Interactions, and their Effect on Skilled Action. And I look really, really forward to his presentation. And please join me in welcoming Dr. Lee with a warm round of applause.
Yeah. Well, thank you very much, Mark. And thank you all for having me. I'm very happy to be here chatting with you all. So really excited to talk to you about some of the work we have going on in my lab. I always like to start talks with some definitions just to make sure everybody's on the same page. So I know this is a cognitive crowd, but just to bring everybody up to speed on some of the things I'm going to be talking about. I want everybody to imagine that they are driving in this car, but not around LSU or Louisiana or even the United States, but in mainland China. So the rules of the road are more or less the same. You drive on the right side of the road. You might have some trouble navigating because you can't maybe read some street signs or anything like that. But you could have Google Maps up or something and do just fine. However, if you cross over into Hong Kong, now you might run into some problems, right? So Hong Kong being a former British colony, they drive on the left side of the road. So now all your usual mappings and all your usual automatic tendencies might lead you astray. So you're going to have to do several things. First, you're going to have to actively keep this rule, drive on the left, in mind. So it's active maintenance of your task relevant context. You're going to have to shift where you deploy your attention, where you scan in your visual field. Oncoming traffic is going to be coming from a different place than usual. So you're going to have to override where you deploy your attention. You're also going to have to override a lot of your habitual and automatic actions in terms of how you turn the car, for example. So if you make a left turn, you're going to be going into a new lane. In addition to scanning for oncoming traffic, that motor program, that motor skill that you have is going to have to be altered a little bit. And let's further imagine that you are making a commute back and forth from mainland China to Hong Kong daily. You're going to have to switch this task context. So you're going to have to do some task switching. So all these kinds of processes, task switching, the active maintenance of your task relevant goals, overriding your pre-potent or automatic responses. These are the kinds of processes I'm referring to as cognitive control or top-down control throughout the talk. And so now I want you to further imagine that you are late for a job interview in Hong Kong. You might imagine that you're better able to carry out some of these cognitive processes. You might be better able to maintain this rule and use this rule to guide your behavior. And I'll be talking about this a little bit later, but there's a lot of experimental evidence that this kind of thing is also happening. So as the title of my talk suggests, I'm also very interested in skilled action, and I love to use the example of golf for this. So, you know, billions of dollars are spent on golf instruction every year, from coaches to magazine subscriptions to books and things like that, all with the idea that top-down control, cognitive control, these rules can actually help learning and performance in a variety of contexts. And that's probably true. If you have a golf coach who tells you to keep your left arm straight in your downswing, you might have a better golf game in a couple months if you practice. However, at the same time, we all have this intuition that when you're the most motivated, it's the time to perform, it's, let's say, the last day of a tournament or something like that, you may not want to be using all these same kinds of processes. You may not want to be using this cognitive control or top-down control. So I always pick on Charles Barkley because of his hideous golf swing, but you might imagine that maybe what he's doing is using too much of this top-down control to guide his behavior when he should be letting his automatic and expert actions take over. So in my lab, the Cognition Control and Action Lab, we're kind of interested in how all these things play together. So how does cognitive control impact the learning performance of skilled actions? How does motivation impact cognitive control? How does motivation directly impact skilled action? What's the combination of all these things? So we often start our investigations using just behavioral experiments. So we do carefully designed behavioral experiments, use computational modeling often to try to get a handle on the behaviors that we're interested in. After that, we often follow up with functional neuroimaging or fMRI to get a sense of the brain areas, the networks involved in supporting the cognitive processes that we're interested in. And after we feel like we have a pretty good handle on the brain networks that seem to be supporting these cognitive processes, we then follow that up with non-invasive brain stimulation in the form of transcranial magnetic stimulation, or TMS, to usually focally and transiently disrupt activity in certain parts of the brain to see how that affects both behavior and brain activity, whole brain wide, basically. So I decided to be a little brave in this talk. So just as outlined, I'm first going to tell you about a particular study that we have a preprint up that's very new out of my lab, looking at how motivation impacts the balance between goal-directed and habitual control. And then after that, the reason I'm brave is I'm going to let you all choose what you want to hear about. So we probably can only get to 2 of these, but there's 5 other projects, maybe even 6, that I will kind of foreshadow now. I will remind you when it's time to vote on them, but I'll let you choose which ones you want to hear about. I know there's a bunch of people from different subfields, so I'm imagining other different things might sound more appealing than others. So again, I'll return to these when it's time to vote, but just to give you a sense of the options. Could talk about a behavioral experiment that came out last year now, looking at how motivation affects skilled action through a cognitive control mechanism or advanced planning of your movements. There's another paper that came out this year, actually following up on that, using neuroimaging to look at how reward impacts the representations of our skilled motor plans. As Mark mentioned, I've done some work looking at why people choke under pressure using both neuroimaging and behavior experiments. So we could talk about maybe what's going on in these scenarios where people are very motivated, but they're actually not doing super well. This fourth one is something I talked about with a couple of you in our meetings. So this one, instead of the action itself, we're going to look at visual-motor decision-making. So if we take a classic economic decision-making task and transform that into a motor decision-making task, how do incentives play a role in this visual-motor decision-making, decisions about where to move. Then finally, for those of you who don't really care about action or movement or skills at all, my lab also is doing a lot of work looking at cognitive control processes in isolation, and especially in concert with motivation. So we can take a look, and I could talk about some work we've done looking at how motivation reward might actually change your work and memory processing. So 5 options. I will be sure to put this screen back up when it's time. But before that, let's start out with that first study that I was going to talk about. How does motivation impact the balance between goal-directed and habitual control? So as I mentioned in that example with Hong Kong and driving on the left side of the road, there's a lot of experimental evidence that reward enhances what's called proactive control or proactive cognitive control. So a typical cognitive control task that's used in this literature is a Stroop-like task or a conflict task, where participants are presented with an image. They have to make a judgment about this image, whether it is a house or a building. Overlaid on that, there will be a word, either house or building, or maybe a neutral string of letters or a nonsense word or something like that. And the typical finding is that because word reading is automatic, if the word conflicts or is different than what the underlying image is, you have problems reporting whether the image was a building or a house. So for example, in this case where a house is overlaid on top of building, you automatically read house and you tend to want to make that house response. You need to use cognitive control to suppress the processing of the word reading and suppress your action in order to successfully respond to building. And the typical thing that folks do is if you give people rewards, you tend to be better able to resist this distraction or overcome this distraction from this incongruent word. And so the typical dependent variable in these studies is reaction time. So this pattern is generally what you see. You're fastest for trials where the word and the image are congruent. You're a little bit slower when the word is neutral. And when the word is incongruent, you have a big cost. You're much slower. And so typically what you see with reward is when you have asked participants to do this and you reward them for their performance, you see a big reduction in reaction times across the board. But you see the largest reduction on these incongruent trials, which need cognitive control to kind of overcome this distraction. So people usually take this as evidence that you're using these cognitive control processes and those are enhanced by a reward. So one problem with this is that response time, reaction time is confounded. So there's this recent study by Adrian Haith and colleagues that showed that the time it takes you to prepare a response isn't actually the same as your response initiation or your RT. So just an example of how they showed that, they asked people to hold on to a manipulandum. And so they're just making reaching movements. They start in the center, location lights up, and they just have to move to it. Their arm is covered. They can't actually see their hand. They just see a cursor. And so on a given trial, you start in the middle, something lights up, you just reach to it as fast as you can. If you look at response time or RT, it'll look something like this up here. So this is their response time distribution. So the dependent variable here is what % of trials have this RT, a cumulative distribution. So at, let's say, 220 milliseconds or so, 50% of your responses are that fast or faster. Okay, so this is a normal kind of profile of response times. However, if you force people to respond at specific times, if you ask them to respond earlier than their typical response distribution, they're still very accurate. So one thing you could do is you can plot accuracy on this y-axis at different times where you force them to make this reaching movement. And what you see is that people are very accurate. So you can get up to close to 100% accuracy at 150 milliseconds in this case, which is much faster than the typical RT, okay? So time it took you to prepare this response and make this response is much faster than your typical response time. Another way of showing that is plotting people's actual response time right here on the y-axis, and how much time, if you force them to go, how much time they need to be pretty accurate. And as you can see, everybody has a big delay in when they actually have their response time and how fast they can actually go if you force them. Okay, so response time might not be the best dependent measure. And so we wanted to look at specifically how reward shifts the balance between goal-directed and habitual actions. And in some sense, they kind of compete for action selection. So using this, again, this example of driving in Hong Kong, if you're turning left, you have maybe competing commands about which lane you turn into. And whichever one wins is the action you're going to take. And so one issue is it's pretty hard to induce humans to make these habitual responses in these kinds of conflict tasks that I was talking about. People are usually quite accurate, 90% plus accuracy often. So you have to infer this inhibition of the habitual action from a slowed response time. And in some sense, your goal-directed response is masking the activity of this habitual response preparation. And so, as I keep mentioning, this can be difficult to assess with conventional paradigms if you want to see how a third variable like motivation impacts the balance between these processes. Okay, so what did we do? We had people perform a fairly classic conflict task called the lsumind task. So on a given trial, participant is going to see a colored circle. If it is one color, they have to press a button with their left hand. If it is another color, they have to press a button with their right hand. You can present this colored circle on either side of the screen. So if you present it on the left side of the screen, for example, and blue signals a left button response, this is a congruent trial. The side of the screen, the location, is congruent with the button you're supposed to press. People are usually pretty fast at this. Or you could present the stimulus on the other side of the screen, so the right side of the screen. Location very much primes the right hand button response in this case. So you're going to have some conflict. If we did a classic response time task, it'd be much slower in this case. So this task has been studied, hundreds, if not thousands of times. So how did we change this up to take advantage of the fact, or to take a look at these habitual responses? So we can actually force people to respond at particular times. So participants who come into this task, they see a fixation cross, and then we give them these equally spaced response time cues. You can also do this auditorily. This is an online experiment, so we did it with just flashes of this stimulus, but you can imagine these are tones. So you get 1, 2, 3, and at 4, you have to press a button. So on every trial, you have to press a button at 2,500 milliseconds or so. So you can imagine trial starts, beep, 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 press a button. And the thing that we are varying as the experimenters is when we show you that stimulus. So we can vary how much time you have to prepare a response before you must make it. Okay, so to give you a sense of what that looks like, what I'm plotting here is a histogram. So this is the number of trials. Remember, people are supposed to be responding at 2,500 milliseconds. People are pretty good at responding right on time. In our actual analysis that I'm going to show you, we only take responses that are plus or minus 100 milliseconds off of this. So well-timed responses. And we can kind of sample in a uniform distribution when we give this stimulus. So we can give it very early, we can give people a long time to prepare that response, or we can give it right before they need to respond and see what they respond when they only have a few hundred milliseconds to respond to the stimulus. So we are essentially controlling their response time. We're controlling how much preparation time they have. And what we can take a look at is accuracy. How well can they respond to the stimulus? Are they tempted to make that habitual response? And the way we model this behavior is with a response preparation model adapted from Hardwick and colleagues. This is also Adrian Haight's lab at Johns Hopkins. And so the model makes a few assumptions, one which I hope everybody agrees are reasonable. Assumes that goals and habits are prepared with separate responses. So preparing a response to the color is a separate process than preparing a response to the location. It assumes that habits are prepared more quickly than goals. So responding to location is going to be faster than responding to color. The exact preparation time it takes to prepare a habit or goal varies around some mean. So you can imagine this is how much time it takes to prepare a response. The goal maybe on average takes about 400 milliseconds to prepare that response. And once a goal is prepared, it overrides the habitual response. Okay, and so we're trying to try to estimate how long it takes people to prepare a goal response or habit response. So we're going to get some mean of how long it takes to prepare a goal, some mean of how long it takes to prepare a habit, and some measure of standard deviation of how variable people are across trials. And so to plot that like I did before, this is just a probability of a response being prepared. So at early time points, the habit, for example, is very likely to be prepared in this case. The goal is less likely to be prepared. But if you give people a long time, it's quite likely you're going to have the goal prepared. Okay. So what does behavior look like in that lsumind test that I was talking about? So over here on the y-axis, I'm plotting accuracy, how well you can respond to the color. So can you press the color accurately or not? As a function of how much preparation time we give you. How much in advance do we give you that stimulus that tells you when to respond? Early on, people are pretty noisy. They're essentially guessing early on. But what you can see in the no conflict case, when they're congruent, when the side of the screen matches the color, people start to become pretty accurate around 200 to 300 milliseconds. They can respond fairly accurately. In this conflict case, where the color is telling you to respond to with the opposite hand as the location, you actually see that people dip below chance and actually make a lot of habitual errors. So if we sample densely at this time point, we can actually see people making these habitual responses, something that you generally don't see in these classic conflict tasks since people are so good. So people are actually making habitual errors at early time points, but if you give them more time to prepare, they're just fine with this. So if you give them 500-600 milliseconds to prepare, they're back at close to 100% accuracy. Okay, so this is just the behavior profile, but what does motivation do? So there are a few possibilities. So remember, just to orient you to everything, so these are the underlying distributions of the goal-directed response in green. The pink here is going to be that habitual response. Remember, goal-directed response are slower than habitual responses. And these lightly shaded lines are when the reward value is low. These dark lines are when reward value is high. So you might imagine that motivation might slow down your habit preparation. You might inhibit the preparation of this habitual response, and maybe nothing's happening to the goal. That would have a certain behavioral profile, okay? That would look something like this. So you reduce these habitual errors by reducing or slowing down the habit preparation. Ultimately, you might expect that what reward is doing is actually accelerating your preparation of this goal-directed response. So speeding up how quickly you can prepare based on the color, which would again reduce habitual errors, but you'd have a somewhat different behavior profile for that. And so we can use our modeling to kind of disentangle which one of these, or if there's some combination of the two that is going on. Just looking at the chats. Okay. So the task was basically that Simon task I was talking about, where we vary the onset of the stimulus. People were playing for cash bonuses, either $1 or $5 on every trial. They had 5 trials in a row of each reward value, but on every trial, we told them what amount of reward was possible for that trial, and then we had one trial. And so for a lot of the experiments I'm talking about today, I will be using reward. I just want to make a note of how rewards work in our experiments. People aren't accumulating money throughout the experiment. Instead, people are told that, and we actually do this, that at the end of the experiment, we pick one trial at random. If they were successful in that trial, they win the associated cash bonus. If they failed in that trial, they don't get the cash bonus. So this kind of ensures that people have to independently evaluate the reward on every single trial. And you can't earn a bunch of money and then stop trying or anything like that. If you want to earn money, you kind of have to pay attention the whole time. Okay, so let's look at behavior. What does reward do to these habitual errors? So again, I'm plotting accuracy, how well you can respond to that color. In blue is going to be those congruent trials where the side of the stimulus on the screen maps on to the color and is the same button. In orange is when there's this conflict. So the side of the screen is opposite of what the color says you should press. And so hopefully what you see again is that we nicely show that people make quite a bit of habitual errors at these early time points. So they're below chance performance. They're actually responding more often based on location at these early time points than the color of the screen. But you quickly recover if you give people around 400, 500 milliseconds. And hopefully what you can see is that we're reducing habitual errors as a function of reward. So low reward value, high reward value, you're reducing the commission of these habitual errors. And so it's kind of unclear just looking at this. Okay, well, is this the habit or the goal? What's actually going on here? So this is where our modeling comes in. So our model pretty faithfully reproduces this behavior. We reduce these habitual errors. And what we are finding is that reward is selectively enhancing or speeding up the preparation of the goal-directed response, okay? So ignore this bottom one for now. But our model is telling us that the goal-directed response is prepared with a faster mean than when it's high value than when it's low value. And so you might see, I might present a few of these depending on which studies you guys talk about, but my trainees are getting pretty fond of doing Bayesian parameter estimation rather than typical null hypothesis significance testing. So instead of p-values, often I'll be showing a posterior distribution of our estimate of some effect. So what I'm plotting here is our evidence that reward is changing the mean. 0 is it's not changing the mean at all. So H is habit. So you can see that the habitual response, basically all of our evidence from our experiment is that it's around 0. We don't have any evidence that it's any different. With the goal-directed response, however, we have some evidence that this mean is speeding up. Okay, so 95% of this distribution is to the left of 0. So 95%, in some sense, 95% confidence that you're speeding up the goal. So you might see these kinds of plots. I'll be sure to try to walk us through those as well. So one important follow-up to this was we did a control experiment where we did this not in a conflict context. So we asked people on alternate blocks respond to the location by itself. So neutral color, the gray on either left or the right. And then in other blocks, respond to the color essentially presented. And so in blue here is just responding to color, responding to location, L, as a function of reward as well. And orange is responding to color. So you're a little bit slow responding to color like you might expect. But what does reward do to these when they're presented in isolation? So what we found is evidence that reward is just speeding up the preparation of both. So it's not that reward is selectively speeding up the goal in any context or color responding in any context. It's specifically in the context of conflict, where your habitual response and your goal-directed response are competing with one another. You selectively speed up the goal and you don't change the habit distribution at all.
Nikita was asking a nice question about, doesn't the model predict increased accuracy, not only around 300 milliseconds, but after as well?
Let me go back to here. So this is the model prediction basically of what people's behavior should look like. So around 250, 300 milliseconds, people are going to be making that habitual response. So they are going to be, their action is going to be pretty poor, but that will rise up pretty quickly. And this is fairly similar to what our behavior profile looks like.
Interesting.
Okay, question. What do you expect to happen if you start with a cash prize and you make errors into punishment? We are running a punishment version of this currently. So we don't have a full sample yet. So far, it looks very similar to this. You might expect, given the large literature on reward and punishment, and reward having approach motivation and punishment having avoid kind of motivation, that you might expect you see something different, you inhibit more maybe in the punishment, but that's not what we're seeing so far at least. So far we're seeing the same kind of thing, that a speeding of the goal-directed response, the speeding of responding to color. We've also run this with an arrow version. So instead of, let me see if I have that. So instead of having a color here, you can have an arrow pointing left to right. So participants are instructed to respond to the direction of the arrow rather than the location on the screen. You see the same exact thing where I don't have the figure, unfortunately, but the goal-directed response in that case is also sped up specifically. Does the response have to do anything with age? We have not tested older individuals yet on this task. There's a bunch of folks here who are very interested in normal aging, so I might collaborate them at some points. We're actually doing a lot of different experiments with this sort of task, looking at basic cognitive control processes like posterior slowing and conflict adaptation and things. It's really nice to be able to actually get behavior out. The commission of actual responses is it's a pretty cool technique. Okay, so to make sure I have some time to talk about the other experiments, some conclusions from this initial experiment. I'm kind of evangelist for these forced response paradigms now. It can really reveal the interplay of habitual and goal-directed responses. You can unmask these latent habits if you're interested in habitual responding. And rewards and motivation, in some sense, sharpen the preparation of goal-directed actions. So they speed up the preparation of goal-directed actions, but they don't do much to the preparation of habitual actions in this conflict situation. So reward selectively enhances goal-directed processing under conflict. Preprint is up on SciArchive, I believe. You should be able to find it if you're interested. Okay, now it's time to vote. I'm going to put these up again and put the poll up. Continue relaunch polling. Okay, so you should be able to vote on anything that you would like. I don't really have a preference. Depending on what you vote for, it might be a smoother or less smooth presentation, given depending on how recently I've talked about these things. Okay, it's tight so far. I'll give everybody a minute or two. So if you haven't voted yet and you're forgetting something, one is a behavioral experiment looking at how motivation impacts skilled action through motor planning. fMRI experiment asking basically the same question: what does reward do to the neural representations of motor plans? How can this all go wrong when you're motivated? So when we're choking under pressure. How this is a fun one. Number 4 is fun. What happens when you're to your motor decision making? Where to move? How do large studies impact that? And finally, I know there's a bunch of folks who do working memory and are interested in working memory and cognitive control in general. What does reward do to working memory processes? So there's still maybe 20 of you who haven't voted. I'll give you another 10 seconds. You still might tip the balance if you vote. If you vote now. Okay, we'll end it there. So results: people want to hear about choking under pressure. And then next was working memory. So I'll do those 2. I'll do 3 first and then working memory. So I'm going to talk, because I get to choose some things, I'm going to talk about the neuroimaging experiment of choking under pressure. If you're interested, maybe I'll allude to the other one at some point. Okay. So choking under pressure, Charles Barkley, what's going on with his golf swing? Experimentally, this kind of idea of choking under pressure or over motivation or over arousal impairing performance goes back quite a long time to these, Yerkes-Dotson's curves around the turn of the 20th century. The basic finding is, for easy tasks at least, as arousal or performance pressure goes up, you get better up to some asymptotic level where you're doing as good as you can. For more challenging tasks, what you see sometimes is that as arousal performance pressure goes up, people get better. But if it's too high, people start doing worse again. So in some sense, choking under pressure is kind of, if you're interested in it, is like what's going on here when you get worse, when you're highly motivated or highly aroused. In the cognitive psychology literature and the behavioral literature, there's kind of 2 overarching theories of what could be going on when you're choking under pressure. They are the distraction, what I'm going to call the distraction theories of choking under pressure, or the explicit monitoring theories of choking under pressure. So the distraction theories of choking under pressure, and both of these appeal to cognitive control mechanisms. So the distraction theory is that in these high pressure situations, you're worried about task failure or what people think, or you're thinking about these kind of goals and what people are, how people are going to judge you or something like that. And that leads to reduced cognitive control, reduced attention to the task at hand, leading to poor performance. Monitoring theories are kind of the complete opposite, and is that in these high pressure situations, people are really motivated to succeed. They try to take too much control over their smooth and automatic actions, and that actually leads to impaired performance. So both of these kind of classes of theories make the same kind of behavioral prediction that, as performance pressure goes up, you're going to do worse. So what I thought to do was to try to use neuroimaging to see if in a particular context, we can kind of distinguish between which one of these theories is more explanatory for a given task in context. So the experiment or the task that we used was kind of this novel bimanual motor task. So it's, I don't know if any of you played that snake game on a phone where you have to navigate a snake to eat an apple and it gets longer. I kind of took some of that code and bastardized it a little bit. And so what people had to do was control this snake across the screen to this large apple that was on the other side of the screen. The way they were controlling it is with these kind of mouse scroll wheels. One hand was controlling the speed of the snake, the other hand was steering left and right. And we could vary the time deadlines and the size of the target to set everybody's accuracy at about 50% after training. So they came in on a day in the scanner, an fMRI scanner. They practiced this task, and then they came back and played with cash bonuses, and we wanted to see how reward, and specifically large rewards, would impact the performance. We did a lot of behavioral piloting to try to figure out a reward scheme that would kind of elicit this kind of choking under pressure. So one trial of the task in the scanner would look something like this. You see a reward cue, you have some fixation for some variable amount of time, and then you try to get your snake over to the apple with some speed and timing constraints. Then you get some feedback, and then you go to the next trial. And so in every trial, it could either be $5, $10, or $40 to try to elicit this kind of inverted U-shaped curve performance. And so all the fMRI data I'm be showing you is from this reward presentation period when they're preparing the responses, but they haven't actually moved yet. So it's not going to be confounded by any kind of error-related processing, seeing yourself go wrong. This is kind of what is the state of the system right before you're about to go. So what I'm plotting here is just accuracy. How often could you get to that target apple under the constraints as a function of reward value? And we could reproduce this kind of inverted U-shaped curve of performance. So people did okay at $5, but they did much better for $10. They got some motivational effect, but at these high value trials, they started doing worse again. So let's look under the hood, look in the brain, see how things are changing at these high reward value trials. What we reasoned was that essentially anything that has to be interfering with performance at some level has to interact with motor cortex, so primary motor cortex, M1. And so we did what's called a functional connectivity analysis, trying to see across time what areas are communicating with motor cortex and how that might differ as a function of reward. So the way you do that is you get across time for every single reward value, you see the activity in motor cortex. So plotted here across time, this is basically activity. And then you can ask the question, okay, what areas across time are correlated, is the activity correlated across time with motor cortex, making the inference that if activity is correlated across time, there's some communication between these regions. And so when we look at $40 trials versus $10 trials, what did we find? Specifically, we saw that on these high pressure trials, I'm calling the $40 trials versus these $10 trials, you saw increased communication between dorsolateral prefrontal cortex and motor cortex bilaterally. So DLPFC being an area of the brain that's known to be very important for things like cognitive control and working memory. So what I want us to note is that this fact by itself, you could take this as evidence of either theory. So I'm going to kind of walk us through how that could be. So let's say you like this monitoring theory where more control is bad for you. You might make the prediction that increased connectivity will lead to more choking under pressure, right? So individuals who don't increase their connectivity will do just fine, and people who are engaging in kind of prefrontal control or motor activity might be choking under pressure more. In contrast, you might expect the exact opposite if you favor these distraction theories. You might say, oh, what's going on is on these high value trials, people are distracted away. In order to overcome that distraction, they have to increase their connectivity. And to the extent that people can do that, they're going to do much better. So increased connectivity might be protective against choking under pressure. And so when we took a look at our participants, this latter trend is exactly what we found. So what I'm plotting here is the extent of choking under pressure. How much worse are you at those high value trials than those kind of medium value trials? On the x-axis here is connectivity. So are you increasing connectivity between prefrontal cortex and motor cortex, or is it decreasing on these high value trials? And what we found is the people who are doing just fine or even getting better at these high value trials had increased functional connectivity between dorsolateral prefrontal cortex and motor cortex. The people who are really choking under pressure, if anything, had a decrease in a breakdown in connectivity between these areas. So the conclusion that we drew from this study was that several large rewards can elicit this paradoxical failure in performance. Functional connectivity between motor cortex and dorsolateral prefrontal cortex is increased for these large reward values where you're not doing so well. However, increased connectivity seems to be protective against choking under pressure, suggesting potentially that folks were distracted, and that's why they're doing worse on these high reward values. I want to make a side note. This is for novice skills. Things might be a little different for experts. We're currently doing some work, doing some long-term training on some motor tasks. But these folks had 1 day of training and then they came back for the rewards. So could be for novices only. Okay. Let's go back. I think we have time for one more. So I believe 5 was the next one. So I think I'm going to just go through it and then maybe come back to questions just to make sure we get through the talk and leave some time for discussion at the end. So Nikita, I see your question. I'll come back to that then. Okay, so what does motivation do to working memory processes? Working memory, the ability to maintain information over short periods of time, is this a fixed or a flexible resource? It's funny, I used this example in one of the meetings today, but I imagine that your phone died and you need to hold on to this phone number. Okay, it's a fairly long phone number. You might be able to do it until you until you find a pen to write it down or something like that. I think we all kind of have the intuition, if this phone number is if someone you're interested in dating or asking out or something like that, you might be better able to hold on to that phone number than if it's someone you don't really care about, for example. And in the literature, there is some evidence something like this is happening. Motivation generally seems to maybe improve working memory performance. But the problem is that it's completely confounded with priority. So what do I mean by that? So typically, a working memory experiment that you might see in these tasks is folks will see a screen like this where there's 4 colored shapes. There'll be some delay, and then one colored shape will appear, and they have to say, did this color change from this display I had previously? Okay, so it's kind of a change detection task. And the different shapes that you see can be, in this case, either circle or square. Squares are worth a lot of money, and circles aren't worth very much money. And typically what you see is that people are better able to remember and report about these high value items than these low value items. So this finding is fairly well established that high value items capture attention and shift your priority, but it doesn't really tell us what happens to the entire resource of working memory. As a side note, anybody who's deep into the working memory literature, I'm not using resources in the variable precision case. So if you know what the variable precision model is and think about resources that, I'm not talking about that. Happy to talk about that after. If that didn't make any sense to you, don't worry about it. I'm going to kind of walk through what I mean here. So a question we're interested in is, how does task motivation entire your global working memory processes? So is the case that if the entire display is worth a lot of money, you can hold on to everything much better, for example. So I like to use this pie analogy. So one hypothesis is that when you're very motivated, when you're very rewards at stake, you can kind of grow the size of your working memory pie. You can hold on to more things. And you're better able to remember everything. An alternate hypothesis is that you have the same size pie, but you can just change how you slice it. You can affect how you're distributing these working memory resources across what you see, but you're not just better globally at everything. So how did we address this? What's the task we used? So we're pretty fond of using what's called continuous report working memory tasks. And so this really lets us get at the fidelity of working memory representations. So for example, we can ask you to hold on to the orientation of a line like this. We can take it away. And like I showed previously, one thing you could ask is, okay, is this the same or a different orientation than one I showed you before? Match and no match, and you can get some accuracy. What a continuous working memory report task will do is instead take away the stimulus, show you a line, and ask the participant to turn it to match what's in their memory. Okay. So this gives us a more fine-grained detail over what they're actually remembering, in that we can calculate how much error do they have across trials from what the actual stimulus was to what they reported remembering. Okay. And so you can take this error and you can plot that in a histogram of sorts. So this is 0 degrees would be your perfect, 150 degrees would be your way off, for example. And so there's some probability of reporting all these. So this is actual data from a pilot experiment. And typically what you see is people are centered around 0. Most of their responses around 0, but there's some variability, right? So sometimes you're way off. A lot of times, most of the time you're like around right. But this is kind of, in some sense, the width of this is the fidelity of the working memory distribution. So you can, for example, calculate on average, what's your error? And that's a measure of how good your working memory is your average error, mean absolute error. Okay, so I mentioned that previous studies, reward is kind of confounded with priority. So how do we dissociate that? So this is the task that we used. We gave people a screen that had a reward value. So reward in the same way we've been using it all the time. In this case, I believe it was $5, $10, or $20, or $1, $10, or $20. And they also got a priority queue. So one side of this diamond would turn white. And that means we're more likely to ask you about the thing on this side of the screen than this side of the screen. Okay, so a classic Posner queue, if you're familiar with Posner queuing paradigms. We give people 2 of these gratings that are of different orientations, so these are different angles. There's a long delay. After a delay, a probe is going to appear, and people have to turn it to match what was in their memory. So we have some trials where we ask you about the queued item So it's a validly queued, a valid trial. But sometimes we ask you about the other stimulus too. Okay, so this would be an invalid trial because we ask you about the stimulus that we didn't queue you about. So in order to do well, in order to get 100% correct to really earn the money, you should hold on to both of these. You might want to take advantage of this queue somewhat, but in order to do well in this trial, you have to have held on to this item as well. So in this case, priority is signaled by this arrow, but reward is this independent thing riding on top of that. And again, remember that our dependent variable here is recall error. So in this case, red is actual and blue is what they responded, and you can calculate some error off of that. And so what you might imagine, to go back to those hypotheses, is that reward is sharpening everything. You're growing this pie. So this is that distribution for these queued items and unqueued items, maybe a better memory. So it's a little tighter distribution for these queued items and these unqueued items. When you're rewarded, you're just better at everything. It's one possibility. Another possibility is that you're changing your control strategy, change how you slice this pie. So on maybe low value trials, this is kind of the distributions you get. And on high value trials, maybe you shift your working memory resources toward this queued item, and that comes at a cost of disrupting this unqueued, your memory for this unqueued item. So hypothetical results. So what I'm plotting here is like this fictitious resources on low value and high value. You might have make the guess that, you know, your working memory is your working memory, nothing changes. That would look like this. So if I'm plotting mean absolute error, how off are you on average across trials? In green would be those valid trials. So you're better at valid than invalid trials. And at the different reward values, you're just doing the same. It doesn't do anything. Alternatively, you might think, oh, you know what? If it's that phone number I really want to hold on to, if it's really important, I might boost everything, okay? You're increasing your resources globally, you get a better performance on invalid and valid trials. It's another possibility. And the final possibility is kind of that change how you slice it analogy. So maybe you have the same amount of total resources, but you kind of get better at one and kind of shift these resources around, right? And that would look something like this. You're better for these high value trials, these valid trials, but on these invalid trials that you're getting actually worse. Okay, so what do we see? I guess the title kind of gives it away. Reward influences the allocation of resources. So our first experiment, that queue that I was showing you, was valid 80% of the time. Okay, so 80% of the time we ask you about the item that the arrow was pointing to. And what we found is that for the valid trials, you get better as reward value grows. So again, mean absolute error goes down. But for the invalid trials, it comes at a cost, right? So you're worse actually for this invalid when we ask about the other item for these high valid trials. Again, this is that Bayesian parameter estimation. So this is looking at that reward by validity interaction. Are these two slopes different? One would be the slopes are the same. All of our evidence is over here virtually that this slope is more negative essentially than this is. So we followed this up with a pre-registered experiment. We didn't have quite that many invalid trials to do some of the modeling I'm going to talk about in 1 second. So we changed the validity. So it's 2/3 of the time we ask you about the one the arrow was pointing toward. 1/3 of the time we ask you about the invalid trial. But we saw the same basic pattern of results. For these validly queued trials where we ask you about the stimulus that the arrow was pointing to, you get better as the reward value goes higher, but you get worse at these invalid ones. Again, based on this entire posterior distribution, all of our evidence seems to be on the case that this is more negative than this. So I mentioned modeling. So you can, there's various ways you can model this. A popular one is what's called a mixture model of working memory recall. So imagine this is just that histogram I was talking about before. In black is what the actual memories are, what your error actually is. In this case, this is a color, but you can center it as, let's say, 0 error. And so the idea of the mixture model is like, sometimes you just don't have it. You're just guessing randomly. So you're equally likely in this red line to be guessing everything. But in the times where you actually have something in memory, it's going to be sharply around the correct item. Okay. So you can try to fit, so that histogram I was showing you, could try to fit that with the mixture model to try to get a sense of how often folks are guessing. And when they actually have something in memory, how sharp is that memory representation? In the modeling that we do, we also include what's called swaps. So remember, there's 2 items. So you might imagine on some trials, people incorrectly respond. The arrow is pointing left. I tell them to respond about the right stimulus, but they incorrectly report the left stimulus. So that's what's called a swap. That would look something like this. So this is the target, in this case color, but imagine target orientation. And this is the one that were presented on the other side. Sometimes they might just respond to that item instead. So this is kind of a binding. So I realize math is scary, so I'm not gonna go into this too much. Just to give you intuition of what the model is trying to fit. So remember, this is kind of the distribution we get. This is just a histogram. How often are you this far off? How often are you this far off? We can fit this data with our model. And what we get out is some parameters. What's the probability that you're actually responding about the target? How likely were you to actually encode that item? We get some probability that you're just guessing randomly. That would be this blue area right here, probability of guessing. We get a standard deviation, so width of this, if you have the memory, how well do you remember it? How sharp is this? Are you really variable, or are you like pretty tightly around the distribution? And finally, how likely are you to have swapped and be responding about the other item? So this is actual data again. This is if we center their responses based on the item that we didn't ask them about. You'll see it's kind of peaked around 0. So sometimes they respond about the other item, but if you center this off of the item we didn't ask about, obviously the error is higher. But sometimes you're responding about the other item instead. So probability of target, how likely are you to be actually responding to the item that we're asking about? What's the probability that you're just guessing? Probability that you responded to the wrong item, and some measure of like how precise your working memory is. Okay, so what did we find? If we look at probability of target here, so this is the probability that you respond to the target. Valid again is going to be in green, invalid is in blue. As reward value goes up, you're much more likely to have successfully encoded and report the target item. The opposite is true for invalid trials. For invalid trials, as reward value goes up, you're less and less likely to actually report the correct stimulus. You don't have the correct stimulus in memory. And if you look at guess rate, you see kind of the inverse of this. So for these valid trials, as reward value goes up, you're way less likely to be guessing and you're actually responding about the target. On these invalid trials, you're just kind of randomly guessing more. You don't actually have it as reward value goes up, okay? The same exact kind of profile was replicated in this 2/3, 1/3 validity experiment. More likely to have encoded the valid stimulus as reward goes up, and more likely to be guessing randomly if on these invalid trials as reward value goes up. Okay, final point, and then on the study also. So this is the experiment we had before. You get this reward and priority queue, you get the queue, then we ask you to respond. So the queue's here as before, it's earlier, it's before encoding and maintenance. So before you put these in your working memory, you get it, you know which one we're likely to ask you about. You could instead let people encode both of these and then give them the priority queue afterward. Okay, so what we're trying to get at here is, does reward affect your working memory encoding, like your selective attention and putting it into memory, or how well you can hold on to it, okay? If reward is affecting how well you can just hold on to it, your maintenance, then getting the queue here should show the same exact behavioral profile, right? So if we see the same behavioral profile when the queue is afterward, we'll say that reward is acting on the maintenance. If we don't see anything, we say reward is acting on encoding. So just to remind you what that previous result looked like, mean absolute error, you're better at valid trials, worse at invalid trials as reward value goes up. If we do that post queue, where we give that queue afterward, we don't see any reward effect. Basically, no evidence of an interaction. So all centered around no change in slope. You see a queuing effect. So people are better at the validly queued item than the invalidly queued item. But we don't see any evidence of reward. So conclusions from this study is that reward influences the allocation, but not the availability of these working memory resources. So there seems to be some fixed upper limit to working memory capacity, but reward is associated with the probability of successfully encoding an item rather than precision or binding errors responding to the wrong, about the wrong item. And once you have it in working memory, reward doesn't seem to do much, okay? So if you've already encoded, reward doesn't seem to do much, but reward affects your encoding strategy in some sense. Okay, so I will stop there. Ooh, how do I get to the end? Where's my end slide? It should be here. So I just wanted to kind of signpost some of the other work that we have going on lab. Happy to chat about anything either now or at a different time if people are interested. I mentioned we're doing a lot of studies with expertise and long-term training with motor control, both using TMS, how people, brain areas that are involved in the development of expertise, and also reward, how does choking to pressure work when you're experts or not. Cerebellum's role in working memory, so classic motor structure, seems to be very involved for cognitive function as well, so we're looking at that. We're doing a few studies with Parkinson's disease, looking at motivation action links and also kind of how cognitive control can compensate for deficits in Parkinson's disease. So just wanted to close by thinking, I wasn't sure what you were going to ask about. So I put a bunch of folks up here. James Brissenden was the first author on that working memory experiment. Tyler Adkins is the first author on that goal-directed habitual experiment, the first one I talked about. I was the first author on the choking depression one, so I didn't put my own picture here, but my face is here, so you see me. And thank you all for listening. Happy to take any questions now. So I'm gonna start with Nikita's. Do you have any thoughts on what physiological mechanisms can affect connectivity in this task? I'm assuming that was the choking under pressure experiment. So physiological mechanisms as in like does increased arousal affect functional connectivity globally? As kind of how I'm gonna read that. Let me see if I can find this slide. So I'm assuming does arousal in general just enhance connectivity globally or something like that? So I can say that it doesn't. So even if let's say it were arousal would enhance connectivity globally, we should see more than just the LPFC. So when we do this analysis, contrasting this $40 to $10 value trials, basically the LPFC, the only other area that comes up even the slightest is anterior cingulate, goes up a little bit, motor to anterior cingulate connectivity. So it does seem to be fairly specific to this interaction. How were the experiments affected with individuals of neurodivergence? So all of the experiments I presented today were on neurotypical individuals, young, healthy adults, typically 18 to 30, 35 or so. So we haven't really tested that. Actually, that's not true. So I'm gonna go back. I don't have, so this experiment, we've tested this with folks with ADHD. Actually, this is kind of interesting. So we tested, let me go back to, let's go to just like a basic, okay. So this is just if you do a conflict task with its forced responses. Remember, we get some habitual errors. If you look at folks with ADHD, either diagnosed or just score highly on an ADHD scale in a questionnaire, you might expect to have more habitual errors, and they do. But the interesting thing is they're just actually much faster at preparing both of these responses. So their entire, I don't know if this makes any sense, but their entire curves are shifted to the left. So they make many more habitual errors, but they recover much faster, such that where normal individuals, like in this case, they're at 75% on conflict trials, 75% accuracy at 400 milliseconds. ADHD individuals are actually like over here. So they can do really well if they have enough time and better than normal individuals. But they have a lot of impairments because one, free response task, they respond much more quickly in general. But specifically their processing is faster and they tend to be very, they respond with what they have. So they tend to make these habitual errors quite a bit more than healthy individuals.
Interesting.
Okay, what software do we use to program those tests? I'm assuming this is the Bayesian analyses. We use several. Most of them are in Stan in R to the Bayesian parameter estimation. We use money as so we typically for most of our analysis are programming our analysis. We're not using any like GUI packages or anything. It's mostly R, Stan, sometimes Python, I suppose. I like Python the best, but my trainees like R. Use money as a reward and motivation to work in memory experiment. I know that money is a highly motivating reward. So do you think you may find different results with a point reward system in terms of money? internal motivation versus external motivation. So as I'll talk about this earlier today with somebody, you can get similar things with points. So points often, if you do your experiment with points, you often see similar effects that you would with money. Money is often stronger. So you see more reward effects if you're using actual cash bonuses rather than points. But you actually see a lot. So if you just give, let's say, auditory feedback, you give a nice pleasant bing every time you do correct. That is also like rewarding to individuals. I don't know if I'd call it, I wouldn't call it intrinsic reward because it is an external reward. So in some sense, money is also arbitrary. It's not like you're getting juice like a monkey, or it's not like we often don't do primary rewards and punishments. It's like this symbolic reward and punishment. So they function kind of similarly. In my experience, money works better as a stronger effect than just points or pleasant sounds. So that's typically why I use it. The nice thing with money too is you can kind of parametrically vary the values. So whereas, I mean, any of these experiments, the working memory experiment, for example, we could use 3 different reward values and see, parametrically it goes up. If you have like sounds or anything else, it's just like present or absent, it can be a little tougher. You can do that with points too. But again, effects often stronger with reward. Go ahead.
Would you expect that this maybe changes if you further increase the amount of the money? So if there's something like a threshold, so if you go incredibly high, like 1,000 or even higher, is there something like breaking apart or making it maybe more efficient?
So I think it depends on the task. I think most tasks would likely, well, it depends on the task. You're going to asymptote out. You can't, it's not just infinite. You can't keep getting better and better. You're going to have some ceiling of performance. If the values are especially high, you're almost certainly going to get choking under pressure. What that value is, if you're using money for an individual, is kind of variable across people. So for the choking under pressure task that I presented, we did quite a lot of piloting to figure out a reward scheme that worked with our population. But I know that if you make it very, like, let's say you do 1 month's rent, for example, almost everybody's going to show this kind of profile. For a task that's even somewhat challenging. But if it's an easy task, like press this button or something, you're just going to get to some ceiling level performance. Jang said, I mean, the cognitive task. What do we do to program the cognitive tasks? Almost everything now is with PsychoPy and Pavlovia for our online experiments, and we recruit our participants through Prolific. The choke under pressure, this study I programmed in Pygame, which is another Python pack. PsychoPy actually uses Pygame. So mostly PsychoPy is actually great. You don't need to know how to program to use it well, but if you do know how to program in Python, you can do quite a lot of things with it. What are the effects of time preparation and response when the presence of the goal or reward is known by participants but is not specified? So I'm imagining that's that first experiment. So let's go back there, here-ish. What are the effects of time preparation and response when the presence of the goal is known but is not specified? Are you asking if they don't know they're specific, if it's $1 or $5, or if it's like 0 versus any dollars, or so I imagine, good question. So we did $1 and $5. I would imagine you'd see something similar with 0 versus $5. We actually, a reviewer actually asked if that was the case for one of them, so we might actually have to run that experiment. I would imagine it looks very similar to this, actually. Typically what you find is that, what I found, at least in, I don't know how long have I been doing reward stuff, since 2012. Especially if you're using 2 values, the specific values don't actually matter that much. If it's high and low, people treat them kind of categorically as high and low, unless you get really big. So this could have been like a quarter and $1, and I bet we would have seen something similar. We tend to use 1 and 5 or 1 and 10 or 5 and 10 because we've been using them a lot. They tend to work very well for these reward effects. But I would imagine if you did $0 versus $5, you'd see something similar. That's a good question. So is not specified? I don't know what would happen if it was like randomly selected after the fact, one versus like 0 versus 1 or 5. I don't know, but I imagine people just have a categorical perception where this is a reward trial, I'm going to try hard. This is not a reward trial, I'm not going to try very hard.
For your last study that you presented, the working memory one, was it exactly what you expected, so that the reward itself isn't influencing the working memory?
Yeah. So so I'm gonna say the things that weren't surprising, things that were surprising, I suppose. So I've been trying. There's been a lot of folks who are interested in working memory that have tried. So this continuous report tasks in the last like 10 years or so, maybe a little bit more, have gotten very popular in the working memory literature. And a lot of people, I know of at least 3 or 4 groups that have tried to use reward to see how to influence working memory and just don't find anything, which I find odd. I was like, you should, this like phone number example, like you should get better. And there's some, if you do these kinds of experiments, or if you're using just like change detection, it seems like people are a little bit better. At least their RTs are a little bit faster. So you might expect working memory is better. So it's always a puzzle. And so I've been working on this probably 5 years, just randomly piloting various versions. And then I had this idea to use this queue. It's like, okay, well, maybe it's not, maybe it's not your global resources, but maybe how you like allocate it. So I kind of thought this might happen, that it'd be this kind of shift in resources. So like I kind of expected to be something like this when I finally got around to one of this exact experiment after, I don't know, 8 other experiments that failed. But the thing that was surprising I assumed it would be in precision. So like the fidelity of your working memory, like how I was expecting you would get tighter if it's high value, and like, you'd be kind of smeared out if you were low value trial. But that's not, I was a little bit surprised to find that was encoding. It's just like kind of the probability that you have it in your memory or you don't. And it's not about how well you're able to hold on to an item. It's like, did you hold on to it or not, right? Like, so it's more like, are you remembering it or did you just lose it? So the thing that's shifting is reward is making you much more likely to remember this one at the cost of dropping this one, rather than you're holding on to this one, but just weakly or something like that. So it's not about like a strong or weak memory. It's like you have it or you don't, kind of. So that was a little bit surprising. Very interesting talk. Thank you for the talk. I'm curious about 2 basic things with my students in mind. You have excellent a priori study hypotheses for both studies, even with OSA registrations. Could I speak about my process of coming up with tests of hypotheses before running a study? And how do you test the goodness of fit, Bayesian model, and the Simon test? Yeah, these are both good questions. So coming up with testable hypotheses. So I suppose that's reading the literature. So, you can have intuitions about how things would work, right? So you might be interested in some phenomenon. Let's say you're interested in choking under pressure, right? So this is how I came to it, right? Choking under pressure, I thought was an interesting phenomenon. Then you have to read the literature and see what people are saying about it. Has people worked on this before? They have. Oh, look, there's like these kind of 2 camps, and there's a 3rd camp I didn't really talk about. It's a little more recent, but and then you say, okay, well, it seems that the people who've been talking about this, thinking about this a lot, have these 2 separate ideas are going on, or multiple, or maybe there's just one and you don't like it, and you have some other plausible alternative that you think of. So I think one of the things that's important to practice, and what I try to instill in my students, both grad and undergrad and all trainees, is as you're reading a paper or some experiment, like don't always take the author's word for it. See their explanation and then try to generate other things that could be going on. Like, what are potential confounds? Could you explain this differently? And everybody, I think, even without much psychological training, probably has intuitions that might differ from what the authors say. And so I'm just kind of constantly in the mode of trying to think of other ways that this could have happened. And then those are kind of candidate hypotheses that you could test, right? Often it can be a challenge to try to translate your hypothesis into like an experimental manipulation. That requires training and probably a PhD. But that's kind of the process of doing that. So reading a lot and thinking deeply about prior results, I think, is what I would say. How do I test the goodness of fit of a Bayesian model in the Simon test? Yeah. So there are a few different ways. Okay, so let me go to one of those. Like, so for example, let's say this one. So this is like our model fit, right? So we do a few different things. One, you use your model to generate and you simulate what people's behavior would look like if your model's parameters were right. And you can just visually compare. 2, you can change what parameters you're fitting, and you can have goodness. I didn't talk about that experiment, but you can have like predictive accuracy. So with these Bayesian models, you can do what's called leave one out predictive accuracy. So you can train your model on all the data except one trial and try to predict that trial and do that over and over and over again and see how much error you have. And then, so typically it's like a model comparison problem. So you build several plausible models, and the one that's the most accurate in predicting your data is the one that you believe in the most, I suppose. So for this reward experiment, for example, you can do kind of like a multiverse analysis in some sense of like, okay, I'm going to let reward change the mean or the standard deviation, and you could see which one fits your data the best, ideally on an independent data set. And then you can go back, collect new data, and fit the model that you think works the best on those. So, I love the adage that, all models are wrong, but some are useful. Like, it's almost assuredly true that your response preparation doesn't look, where is that? Just like this. There's probably a lot more going on than just these two means and standard deviations running around in your head somewhere. But it might be useful to describe what's going on with habitual and goal-directed responses, for example. So they're all kind of a fiction, and you can try out iteratively. I mean, again, ideally with independent data set, iteratively try out different models to see which one is has the best predictive accuracy, and then go with that one. So admittedly, this one, especially this reward experiment, it's not perfect. Doesn't capture everything, for example. These aren't, where's the, so it's not perfect. It's pretty good. Other experiments that we've done are actually a lot better with this paradigm. Reward is a little bit fickle, but yeah, you test this against other models, basically. Other models that don't, maybe you can test, and you can also test it against a model, for example, that doesn't let reward vary, right? So that's essentially what this is. So 0 would be the mean doesn't change at all. And, we have way more evidence for a model where the goal is faster, for example. Kind of like training validation sets. Yeah, that's the ideal case. It can be always tricky to, fit a million models to your data, to one data set, and then declare victory when one fits best. You don't want to overfit your data. Other questions or comments? Or does anybody want to hear about another study?
Oh, well, that's tempting. I have a sort of short series of interrelated questions.
Sure.
If another study's on the books, I know maybe we need another poll.
I mean, we have 15 minutes. I can relaunch the poll, but if people want, I'm happy to just stick around for a little longer. But go ahead and ask your questions though in the meantime.
Okay, my questions are about choking under pressure and the connectivity between dorsolateral prefrontal cortex and M1. And so that was increased, and I was wondering, so that was a whole brain analysis, not restricted to any network. Okay, and then, so related to that, like, so what could, I guess what might be, is there an application that could be used to help people with choking under pressure? I know that you do brain stimulation, for example. I have an interest in that also. And that's a phenomenon. I mean, I think of it, I work with people with aphasia who talk about the communicative pressure and talk about choking. And also, like students with testing anxiety, for example.
Right, yeah. So we haven't done any intervention work, but a lot of folks have, specifically with test anxiety and choking under pressure. Things that can typically help. So I'm going to start, maybe I'll start with test anxiety. So there's a study, it's on Bilog's lab. I can't remember who the first author is. So they had actual college students who had math anxiety for their math exam. Two groups. Just before the final, they had folks who reported having test anxiety and folks who didn't. If you were asked to just right before the test, like you go to the exam room, the first page of your final exam says, write out all your worries and thoughts about failure. Just write them down on this piece of paper. So just expressing that worry kind of externalizes it, and it's like not in your head anymore, it seems like. And especially people with test anxiety seem perform much better on that math test. So I think they did that in 2 separate samples, if I remember. So just journaling or saying out loud what your worries are in the moment, doing a little self-talk can actually, seems like it has some experimental support. The other thing that I've seen experimentally that has seemed to work is training in situations that mimic the pressure that you're going to be under when you perform. So for example, you can have in a lab, you can have people come in to play some game or something like that. And you could say, okay, we're going to videotape you and I'm going to be evaluating your performance. And you're playing with a partner to earn the $100 and your partner just went and they did great. And now it's all riding on you. And you can like load up all this kind of social and monitoring pressure on them. If you let them practice in that situation where it's like, okay, when you're training on this task, I'm gonna be watching and evaluating your performance and here's a monitor and you're gonna be playing with this partner and look how good they're doing. If you practice in that situation, when you come back to that for a performance, you tend to do just fine. The tricky part about that is it's hard to train in a lot of hyper situations. So if I'm gonna go play in the Super Bowl, I can't really mimic that situation. So as best as you can do that is good. So anecdotally, God, what was his name? There was a basketball coach who I think it was Texas A&M in the 80s, maybe. Their team was the worst free throw shooting team in the country, among the top 5%. And so what he did is in practice, he would stop practice at random times in the practice. He'd ask one person to shoot a free throw. If that person missed, the entire team had to run for like, some kind of sprints or something like that. So kind of mimicking this like kind of random high pressure situation. And the following season, they were like, I think top in their division or something like that, or top in their league of free throw shooting. So anecdotal, obviously, but like trying to mimic in the practice scenarios what that's going to be like. For patients with aphasia, feel pressure speaking, I mean, journaling would help, but that's obviously if you're not going to journal every time you speak, right? So that's a tricky situation. So I would say practice. You just have to do it. It would be the thing that I would suggest, I suppose. I followed up on this choking study with some brain TMS, trying to disrupt that DLPFC region. I didn't get a full sample, but disrupting it just made everybody way worse at the task. If you're choking, you just are really bad now at everything. If you weren't choking under pressure, you look like you're choking now. So taking that offline for these novice performers, at least, is just bad for you. So you kind of need this extra control for these novices. You need to go back and, I don't know, I'm never going to collect more data, I guess, but maybe I should just write it up and publish it.
We have one more question in the question room. Are you actually rewarding people with cash?
Yeah.
Jen Honzinski, thoughts about showing them the money and potential effects on your results?
Yeah, so in person for these experiments, we always show them the cash like in front of their face right before. And we say, hey, you're going to play for cash bonuses. This is real. This is money that could be yours. Just because, especially psychology students that think you're tricking them or something. But we actually do pay them at the end. Online, we can't obviously show them money, but there's a bonus system for most of these online payment systems that you can give a cash bonus. So we actually do pay them. We actually do choose a trial at random. If they got it right, we actually do pay them that money. So I typically, the reason we show them the cash was a lot of times for these choking and pressure experiments to like really show them like, hey, this $41 bills could be like, gonna show them the stack, try to, there's a lot of tricks for this. I didn't really talk about it, but money by itself it can be kind of hard to get these choking effects. So you have to kind of, anybody who's interested in it who wants to use money by itself, I suggest piloting extensively beforehand and finding a paradigm that works. Because it's not just the money. I firmly believe it's not just reward value unless it's like really big. It's kind of other things as well.
We have a question from Heather, like the raised hand.
Yeah. Yeah, I was just wondering if there's been any comparisons behaviorally and neurally about like choking under pressure versus stress about something else, like task irrelevant stress that might harm performance or use cognitive resources. Has there been any comparison of those two?
Yeah, so I haven't seen anything that's directly compared like a cold pressor, acute stress, or something like that. The ones I've seen that compare different stressors has been kind of more monitoring pressure, like someone's evaluating your performance versus just cash or like money. So like reward motivation versus someone like watching you or evaluating performance, evaluative pressure. There's only been one or two studies I've seen. Those suggest that if it's evaluative pressure, let me go back to that. Those two, actually, no, I can go here and just click the button. Yeah. maybe I can't. Maybe I'll just say it unless I can find the choking slide really quick. Here we go. So those studies suggest that if it's reward pressure, you might see more of these distraction type effects. But if someone's watching you, you might get more of these monitoring effects. In terms of I think the tricky thing is in a particular situation, it's kind of hard to disentangle which ones are going on, but you can do some kinds of things to see. You can do like kind of thought probes and things like that to try to get at it. And it suggests it's kind of maybe different source of pressure might have different effects. I think in general, most of the time, probably both of these things are going on when you're choking under pressure. It's kind of this double whammy where you are trying to use more of this cognitive control resources, like I'm showing in this, the task I showed, this choking under pressure task. You're like, you want to allocate more control, but like there's a lot of studies showing that like acute stress selectively impairs cognitive control processes. So you might also get distracted, right? So you're trying to use these resources that might actually be more impaired under stress. In virtually all scenarios, I would imagine that it's probably some combination of these two, but in particular experiments, you might tilt the balance over from one to the other, I think. Okay, I thought I saw maybe something else.
Yeah, there was one more question from Arendt van Germaat.
I think that's the same question. Do you think we'd get the same choking if stressor is high stake evaluation instead of money? Yeah, kind of like what I was saying. I think, yeah, thank you. Yeah,
exactly.
Great minds think alike, right? Okay, so we have 5 minutes. I could do number 4 since people voted for it. If that sounds good to people. Should I just do it? Okay. I could do this quickly. I think I could do it.
I think it's good.
So these are all like kind of non sequiturs from one another because they're kind of very different experiments. So I'm going to start with the story of William Tell. I'm assuming most people are familiar with this. He had to shoot using a crossbow, shoot the apple off his son's head, or else they both be put to death. So I want us to like keep in mind, if you're William Tell, like where do you aim? Okay, because it's a potentially very bad situation that could happen, right? Okay, keep that in the back of your mind. Completely separate question. I want you all to think about this economic decision-making question. Which slot machine do you play? So if you play a slot machine on the left, you have a 50% chance of losing $10, 50% chance of winning 10. If you play the slot machine on the right, you have a 90% chance of losing $100 and a 10% chance of winning $1,000. You can drop in the chat which one you do. This is 1, this is 2. Which one would you, which slot machine would you want to play? 1, 1, 1, 1, 1, 1. Everybody says 1. Okay. Most people say 1. Classic finding. Everybody says 1. If you calculate the expected value of a poll, it's actually $5 here and $10 here. So if we're all like ideally trying to maximize money, you should play the one on the right, but nobody chooses that one. So the optimal decision is to maximize expected value. You want to do this one, but there's a whole host of bias and heuristics that lead people to behave suboptimally in these economic decision-making tasks. One of them is loss aversion. So classic finding, coming under some fire recently, I suppose, but still very reputable global in the lab, that an equivalent gain, so this is value or how good it feels or how bad it feels. A $50 gain doesn't feel quite as good as a $50 loss hurts. So we're kind of biased. That's probably a reason that most people choose this one left. Losing 100 feels worse than winning 100. Okay, so another kind of bias or heuristic that people have in these economic decision-making games. Imagine I now present you with like 10 or 20 different slot machines you can play. You could try them all out, but typically what people do is they pick one that they think is good enough and just satisfies and just do that one over and over again. So instead of sampling all these to see what the win rate is, they find one that's pretty good and they just keep playing it over and over again. Satisfies. Okay, back to William Tell. What does this have to do with William Tell? So his decision about where to aim is a decision-making problem, and it's a planning problem, a motor planning problem. He could choose to aim at the center of the apple. He might hit the apple. He might hit where he's aiming, but there's going to be some variability associated with that choice. you have maybe 40% chance of hitting the apple if you aim there, 50% missing, and like 10% of something really terrible. You could choose to aim somewhere else. That's going to have some other probabilities, right? And you could calculate an expected value after this, okay? Depending on how much you value hitting the apple, missing, and this other option, right? So Trommershauser and colleagues basically had this insight that this is equivalent to those economic decision-making tasks. So instead of, you can think of these as different slot machines, and essentially you have infinite slot machines. Choosing where to aim is choosing a slot machine. So you can have people play this kind of game that's actually a vision motor decision-making task that's equivalent to choosing between a whole bunch of games. So this is the kind of thing participants would see on the screen. You have to reach out and touch this touch screen. If you hit this area, you win $1. If you hit this area, you lose $10. If you hit the middle, you gain 1, lose 10, so net -9. And if you're out here, nothing happens, right? So you can have people do these speeded reaches and decide where they're going to aim. And so based on a lot of evidence from the motor control literature, there's this idea that your motor system optimally can minimize a whole bunch of different kinds of costs. So biomechanical cost, jerk, motor variability, all these things. So it seems that your motor system is fairly optimal at balancing the costs and benefits. And so these folks thought that, okay, maybe if we transform these economic decisions into motor decisions, people would behave more optimally than they do in these classic economic decision-making tasks. And that's essentially what they found. So this paper's been cited, I don't know, hundreds of times at this point. So one thing you could do is, so these are those circles I was talking about, reward circle, penalty circle. What I'm plotting here is like a value landscape. So the top of this is earning, if you aim there, you're going to earn the most money given some motor variability. And this down here, obviously, you're going to lose a lot of money. So for every aim point, you can calculate how much expected value there is. You can have people actually reach out to this display over and over again. You can get some sense of their motor variability. And given their, so these dots are like little endpoints of where they actually touched on different trials. And you can calculate what would be optimal for each person. And lo and behold, what you tend to see is that this is the optimal prediction of where they should aim. This is where they actually aim. And people, these are individual participants in different sessions. People are seem pretty optimal, okay? Seems to be this kind of one-to-one mapping in this vision motor decision-making task. This always bugged me. Like, what about William Tell? Like, what about if it's like your son that you should, like that's, and there's especially a lot of evidence that, not a lot, there's a few papers showing that people who are more loss averse tend to choke under pressure more. So what if it's like a really big value? Are you still going to be fine? And one of the shortcomings of the prior work is they didn't do any model comparison they were talking about. They basically had this optimal model. They looked at behavior and said, oh, look, they're pretty correlated, but they didn't test it against alternative plausible hypotheses. So that's what we did. We thought, oh, maybe if we incorporate loss aversion, it might be that people look more loss averse if you actually put that into your models. That was our initial thought, at least. So we had people play this reaching task. We showed them the penalty and reward values. There's some delay. You press the space bar. At some random time, its configuration is going to come up on the screen. You have to reach out and touch somewhere on the screen. If you're in the reward part, you get the reward. Penalty part, you get the penalty. Both, you get some combination of the two. So on the first day, people came in. They were just reaching to a single dot to get a sense of their motor variability. How good are you at reaching a single point? What's your variability around that? And we introduced them to the idea that there would be reward and penalty regions, but they weren't actually playing for cash bonuses. They came back. They did this again with actual cash rewards and penalties. Crucially, in this experiment, we had you could have an equal loss penalty ratio, 1-to-1, or you can have large penalties. We also varied the reward value, but essentially the penalty reward ratio is what came up. So we have this optimal model that I talked about. You could get a sense of people's motor variability from training. You can calculate based on that for each individual, where should you aim to earn the most money? And let's say for this person's here. You can incorporate loss aversion. So we can have them do a loss aversion task separately with normal, or let's say, shouldn't say normal, classical economic decision-making tasks. You can measure their loss aversion, or lambda, I'm calling it here. You can multiply that by the penalty. So say, okay, this penalty, you're very loss averse. This penalty is actually bigger than -5, or it's -8 for you. You can calculate based on that loss averse model, where should you aim if you're doing this optimally based on some loss averse idea. And for everybody, for loss averse, you're going to shift away from the penalty because you don't want to get it, right? If you're a loss averse person. Like I mentioned before, you could do this model comparison. So you can do leave one out, predictive accuracy. Let's say your model says this person should aim here. You can calculate some sort of error based on where they actually aim. And let's say the loss averse model says aim here. We would say, oh, this one's doing better at explaining my participant's behavior because it's closer to all these points. There's less error. Okay, so
quick summary, exactly. Yeah.
Oh, go ahead.
Quick summary. We are running over time a little already.
Okay. I mean, I'm happy to stop. I thought this was just extra time. But
you should.
So I could just finish up. I can't hear your applause anyway, so it's okay to not have the applause at the end. But anybody who needs to leave
can just leave if they need to, and
Right.
those who want to hear it can stay.
Yeah, thank you for coming, everybody. It's really fun. I had a good time talking. Hopefully people got something out of the talk. Okay, so I'll finish up quick. So what we're finding is, or what we found initially is that, so in green is this optimal model, in pink is this loss averse model. This is that leave one out predictive accuracy. This is like how much error there is. You have less error for the optimal model. So people are, this seems to be a better explanation as loss averse model. So this is like how in millimeters, how far away is our prediction from actual performance? It's like fairly good for the optimal model, but like pretty bad for the loss averse model. But what we noticed in the first iteration of this experiment, so if this is that configuration, optimal says aim at this triangle, loss versus aim at this square, people tend to be aiming close to optimal. But when the reward and penalty values were really big, people weren't aiming anywhere close to optimal. So they were not optimal. And so based on some initial experiments, we said, okay, well, people aren't doing this optimal thing. What about the satisficing idea? So we developed the satisficing model. So if the penalty is 0, just aim at the center of the circle because there's no penalty. Otherwise, don't do any calculation, just aim at the middle of this reward area. So like avoid this penalty, aim at the middle, halfway between there. That's a spot that's good enough. And when we did this model comparison, we found that this satisficing model fit way better than either the optimal model or this loss averse model. And specifically, so each one of these bars is individual participants. If this is like the evidence for the optimal is in gold, if it's above this line, if it's below this orange line, it's evidence for the heuristic model. At these relatively low values, people seem pretty optimal. But when you go to these high values, everybody seems to be adopting this heuristic. So people are not optimally integrating anything. They're just like, oh, pick a spot and aim at it. That's good enough. So kind of casting, we kind of think that the people aren't really optimal at all in these decision-making tasks. You can't get away from these biases and heuristics. You're just governed by other ones. So it does seem that you're like not loss averse when you go into this motor system, right. But especially when the money's big, you just do something else that's also not optimal. Excuse me. Is this choking under pressure? Could be. I kind of think people adopt like a kind of heuristic strategy all over the board. But our evidence is consistent with people are doing this more at the high value. Okay, that's that last one. Thank you, everybody. I know that was a bonus talk.
Exactly, and we got a good comment from Arend. So he's mentioning, so it is framing. This had been shown in risky and less risk medical treatment decisions.
Yeah.
Interesting.
Yeah. So I think I don't think you're getting away from these bias and heuristics.
Right.
It might change which ones are like operative depending on how you frame, like exactly like Arend was saying. So, you know, there's a lot of, in classical economic decision making, depending on how you frame the problem, you can like shift people's biases a little bit. And I think this is just another one of those. It's not like, I don't think we should like transform all these decisions to motor decisions. People are going to look great. It's like, they're just going to have other problems.
Right.
Personally.
Yeah.
People differ. Reviewers had a really hard time, especially people who really like this model, like didn't like this very much, but it's out now. Psychonomic Bulletin Review 2021. I think it's pretty solid. We have replication experiments. I mean, we considered a bunch of extra models that people asked us to consider, and our heuristic fits the best. People are satisfied and using this heuristic, I think, at least.
And I'm very excited because I remember as we met last week that you were pretty curious and also excited about the study that you presented at the end.
Yeah. I wanted to, I really wanted, I was telling people when I was talking to them before that like, that review process sucked and I was really upset about it. And I was kind of sick of that project. And then I was preparing, I gave a talk a couple months ago and I was looking at it, I was like, I'm not even gonna let people vote on this one talk. But then I was looking at it, I was like, you know what, actually, this is a really good study. Like, this is a really good study. It's really nice. It's really clean. Like I'm kind of back on board with it. I want to talk about it again. Because I'd like presented it right before we submit, like 2 years ago. I'd presented about it a lot and I was super excited about it and just kind of got beat down by the review process. And now I'm like, no, this is good. This is a good experiment or a good set of experiments or whatever.
And the people really liked it when we look at the comments that saying for me, beside of the initial included talk portions, but then also the extra one, and that so many people are still hanging out with us. It's always a good saying.
That I was actually equally happy to talk, like more or less equally happy to talk about all 5 of those. I like all my, I don't know, I like what my lab's doing. The stuff that doesn't work, I'm not putting as a choice. But yeah, it's really fun, really fun.
And
Thank
before,
you so much. It was really interesting.
Yeah, I appreciate it.
Before I forget it, to thank you for this great talk on behalf of the executive committee board from all of us. And I learned a lot today and I got very inspired, and it looked like other people as well. And I look forward to further talks in the spring from our Mind series. And I also look forward to talk more with Taras in future about his great research. And he got me so excited last week. And I know that wasn't the last time. Thank you so much for all people who attended today. And again, a big applause for Taras. And I hope you all have a great rest of your evening. And I'm already excited for the next events and seeing you guys again somewhere in conferences and so forth. Thank you guys. Bye.
Thank you. Talk to y'all later.